Hi everyone, welcome back to my channel. In this video, we are going to solve CFSE, that makes Crystal Field Stabilization Energy GATE previous year questions from 2000 to 2012. And also I have explained CFSE theory part. That video link I have mentioned in description. Please go through that. Now we will solve the question. Question 1 asked in GATE 2000. The complex with the maximum crystal field stabilization energy, that means CFSE, is here 4 options given. Option A COCl4 2 minus, option B COH2O6 2 plus, option C COF3H2O thrice, and option D COF6 3 minus. Now we'll see the solution. To compare the crystal field stabilization energy CFSE, determine the oxidation state, d electron configuration, geometry, and ligand strength. Now we'll see the solution. First we have to remember what is the formula for CFSE. For octahedral complex, CFSE is equal to 0.4 into NT2G minus 0.6 into NEG whole into delta naught. Here NT2G is equal to electrons in T2G and NEG is equal to electrons in EG. And for tetrahedral complex, CFSE is equal to 0.6 into Ne minus 0.4 into NT2 into delta T. Since delta T is equal to 4 by 9 delta naught, convert all answers into delta naught for comparison. Now, we will see the option A, COCl4 2 minus complex. In this, we will solve it as step by step. We will see in step 1, we will check the oxidation state for this complex. Let oxidation state of CO is equal to X. Here, X plus 4 into minus 1. 4 into Cl charge is minus 1. That is equal to, and whole that complex charge given, that is minus 2. So X is equal to plus 2. CO oxidation we will get it as a plus 2. Now in step 2 we will see the electronic configuration for cobalt. Cobalt molecular weight is Z is equal to 27. So CO is equal to argon into 3D argon 3d7 4s2 is the electronic configuration for cobalt. Now cobalt oxidation state is plus 2. So CO2 plus is equal to argon into 3d27. Here we remove 2 electrons. So we will get a d7 configuration here. Now we'll see the nature of ligand. Here the ligand is given as a Cl. A Cl minus is a weak field ligand. Weak field ligand gives rise to high spin complexes. So geometry is tetrahedral here. Now in step 4 we will see the electronic arrangement. For tetrahedral, lower level is equal to E, upper level is equal to T2. For D7, E4 and T2 3 we will get the electronic arrangement. So electrons in E is equal to 4 and electrons in T2 is equal to 3. Now in step 5 we will calculate CFSE. For CFSE is equal to 4, that is electrons in E orbital. 4 into 0.6 minus electrons in T2 orbital is 3. 3 into 0.4, that into delta T. So you will get as a 2.4 minus 1.2 delta T, that equal to 1.2 delta T. Now convert into delta naught. 1.2 into 4 by 9 delta naught, that is equal to 0.533 delta naught. Now finally we will get as oxidation state is plus 2, electronic deconfiguration is T7, high spin tetrahedral, and CFSE is equal to 1.2 delta T, that is equal to 0.533 delta naught. And now we will see the option B, COH2O6 2 plus complex. Here we will calculate oxidation state. Here water is a neutral ligand, so we will get a +2 oxidation state. In step 2 we will see electronic configuration. CO2 plus. This already we have discussed earlier. So CO2 plus we will get it as a 3d7 oxidation state. Sorry, 3d7 electronic configuration. In step 3, we will see the ligand. Water is a weak or intermediate field ligand. Hence, it is a high spin octahedral. So, in step 4, we will see the electronic arrangement. For high spin D7, you will get T2G5 and Eg square. Therefore, T2G is equal to 5 and Eg is equal to 2. Now, in step 5, we will calculate CFSE. CFSE is equal to 5 into 0.4 minus 2 into 0.6 into delta naught. That equal to 2 minus 1.2 delta naught. So 0.8 so you will get a 0.8 delta naught. Finally, you will get the oxidation state +2, electronic configuration D7, high spin octahedral. So CFSE is equal to 0.8 delta naught. Here why you have calculated directly delta naught means this complex is a octahedral complex H2O6. Earlier complex is a tetrahedral complex that's why you have first you calculated CFSE in delta T, then you have converted it to delta naught. Now we will see the option C, COF3H2 thrice. Here step 1 we will see the oxidation state. Here water is equal to 0, fluoride is equal to -1 charge. So x plus 3 into -1 is equal to 0. So x is equal to +3. In step 2 electronic configuration for cobalt 3 plus, for electronic configuration is 3d6, means d6 configuration. Now we will see the ligand nature in step 3. F- is a weak field ligand, therefore high spin octahedral. In step 4 we will see the electronic arrangement, that is high spin D6, so T2G4 and Eg square. Hence T2G is equal to 4 and Eg is equal to 2. Now in step 5 we will calculate CFSE, that is equal to 4 into 0.4 minus 2 into 0.6 into delta naught, that is equal to 1.6 minus 1.2 delta naught, that is equal to 0.4 delta naught. Finally, you will get the oxidation state +3, electronic configuration is equal to D6 and high spin and octahedral. Here CFSE is equal to 0.4 delta naught. And last option D, COF6 3 minus complex. Here oxidation state is x plus 6 into -1, that is equal to -3. So x is equal to +3. And step 2 we will calculate electronic configuration. So CO3 plus is equal to 3d6 and d6 configuration. And step 3 we will see the ligand nature. Here F minus is a ligand. Here F minus is a weak field ligand, therefore high spin octahedral complex. In step 4 we will see the electronic arrangement T2G4 and Eg2. We will get as an electronic arrangement. Now we will calculate the CFSE. In step 5 CFSE is equal to 4 into 0.4 minus 2 into 0.6 into delta naught, that is equal to 1.6 minus 1.2 delta naught, that is equal to 0.4 delta naught. Finally, you will get oxidation state is equal to +3, electronic configuration is equal to D6, high spin and octahedral. So CFSE is equal to 0.4 delta naught. Now we will compare all the complexes. Here complex COCl4 2 minus, oxidation state is +2, d electron configuration is d7, geometry is tetrahedral, spin state is high spin, and CFSE is 1.2 delta T is equal to 0.533 delta naught. Here why they have first calculated delta T, This complex is tetrahedral, that's why then they converted into delta. And second complex COH2O6 2 plus. Here oxidation state is plus 2, d electron configuration is d7, geometry is octahedral, spin state is high spin and pointed delta knot. And third complex COF3H2O thrice. Oxidation state is plus 3, configuration is d6, octahedral geometry, high spin state and zero point 0.4 delta knot CFSE. And the fourth complex COF6 3 minus, here oxidation plus 3, electronic configuration d6, octahedral geometry and high spin state, so CFSE is zero point 0.4 delta knot. So here the correct answer is option B, COF6 3 minus. Now we'll move to the second question. This asked in GATE 2005. The magnetic moment of the complex K3COF6 is 5 mu b. The total stabilization energy will be, here for option given, minus zero point 0.4 delta naught. Option B is minus 0.4 delta naught plus P. Option C is minus 2.4 delta naught plus 3P. Option D is minus 0.8 delta naught plus 3P. Now we will see the solution. Here for K3COF6, the complex ion is COF6 3 minus. Now we will find oxidation state of CO. X plus 6 into minus 1, that is equal to minus 3. So X is equal to plus 3. So CO3 plus is equal to D6 configuration. In second, use magnetic moment. Here given mu is equal to 5 mu b. Using mu is equal to root of n into n plus 2 mu b formula and substitute values. 5 is equal to root of n into n plus 2. This gives n is equal to 4 unpaired electrons. So CO3 plus is high spin d6 because F minus is a weak field ligand. Octahedral high spin d6 arrangement T2G4 Eg square. Now calculate CFSE. For octahedral complexes, each T2G electron contributes minus zero point 0.4 delta naught. Each Eg electron contributes plus zero point 0.6 delta naught. So CFSE is equal to 4 into minus zero point 0.4 delta naught plus 2 into plus 0.6 delta naught. That is equal to minus 1.6 delta naught plus 1.2 delta naught, and that is also equal to minus zero point 0.4 delta naught. Now in step 4 we will calculate pairing energy. For high spin d6 has one paired set of electrons, that is plus p. Therefore total stabilization energy is equal to minus zero point 0.4 delta naught plus p. Hence the correct option is here option B, minus zero point 0.4 delta naught plus p. Now we'll see the third question. This is asked in GATE 2006. The series with the correct order of increasing crystal field splitting energy delta naught in their complex is, here four options given: I minus less than PR3 less than CH3 minus and less than CO. And in B, PR3 less than CH3 minus less than I minus and less than CO. And in option C, CH3 minus less than PR3, that is less than I minus and less than CO. Then option D, I minus less than CH3, that is less than PR3 and lesser than CO. Now we will see the solution. The question asks for the correct order of increasing crystal field stabilization energy delta naught for ligands. This is determined by the spectrochemical series. See, this is the order of spectrochemical series. I minus P less than Br minus Cl minus F minus. These are weak field ligands. OH minus H2 and NH3. Neutral ligands En, NO2 minus En minus and CO. These are high spin ligands. Sorry. These weak field, strong field ligands. Now, now we'll see among the given ligands, I minus Ag is the weakest field and PR3P trialkyl phosphine. This is stronger than amides, good pi acceptor, so strong ligand. And CH3 minus is a strong sigma donor but weaker than CO in terms of producing delta. And CO is equal to strongest field ligand. Thus, the increasing order of delta knot is I minus less than PR3 less than CH3 minus and less than CO. So, here the correct answer is option A. I minus less than PR3, that is less than CH3 minus, and that is less than CO. I hope you understood this concept. If you like this concept, please like, share and subscribe to my channel. In next video, we will solve some more previous year questions. Thank you. Have a good